Good day everyone. This is Miss Seleni Anilongo and I will talk about the acid and base in organic chemistry. The key to understand organic chemical reaction is knowledge of acids and bases. When considering a reaction, you need to ask three questions. Where is the acid? Where is the base? How can the acid react with the base? Whether a molecule acts as an acid or a base in a chemical reaction largely depends on its characteristics. There are three significant molecular characteristics that affect acidity and basicity. The most important is the compound's primary functional group. A second factor is the inductive effect caused by the presence of additional functional groups. And the third factor is the delocalization or resonance effects of the electrons in a molecule. There are three major classifications of acids and bases. First, Arrhenius theory. Second, Brostad-Lowry theory. And the third theory is the Lewis theory. In 1884, the Swedish chemist Svante Arrhenius proposed two specific classifications of compounds, the acids and base. His theory states that a stable ionic compound that is soluble in water will break down or dissociate into its components ion. Arrhenius' theory stated that an Arrhenius acid is a source of hydrogen ion and Arrhenius base is a source of negative hydroxide ion. The Arrhenius acid-base theory provided a good start toward understanding acid-base chemistry, but it proved much too limited in its scope. In 1923, chemists Johannes Nicholas Bronsted and Thomas Martin Lowry independently developed definitions of acid and bases based on the compound's abilities to either donate or accept protons. They developed a more general acid-base definition than that of Arrhenius. The basis of their acid-base definition is that in a reaction a proton transfer between reactants. Thus, acids involving a transfer of hydrogen ions are sometimes called proton acids. The second theory stated that a Bronsted-Lowry acid is a proton donor and a Bronsted-Lowry base is a proton acceptor. For example, in this reaction, HCl or the hydrogen chloride is the acid because it is the source of protons or hydrogen ions. NaOH or sodium hydroxide is a base because the hydroxide ion is the proton acceptor. The following reactions further illustrates the Bronsted-Lowry acid base definition. The reaction below is labeled to show the conjugate acid and conjugate base. A hydrogen of sulfuric acid or the H2SO4 is the acid, and the nitrogen of ammonia or the NH3 is the base. They react to form the hydrogen sulfate anion or the HSO4 and the ammonium ion or the NH4 positive. The ammonium ion is the conjugate acid or ammonia. The bisulfate ion is the conjugate base of the sulfuric acid. Like Bronsted and Lowry, Lewis defined acids and bases in a broader scheme than Arrhenius did. Lewis noted that there are a number of reactions that look like acid-base reaction but do not involve the transfer of a proton. Instead, they involve the interaction of a pair of non-bonding electrons. From that observation, he defined an acid as a molecule that forms a covalent band by accepting a pair of electrons and a base as a molecule that forms a covalent band by donating a pair of electrons. Lewis' theory stated that a Lewis acid is an electron pair acceptor, while a Lewis base is an electron pair donor. This is a reaction between ammonia and boron trifluoride. Since there is no transfer of hydrogen atoms here, it is clear that this is a Lewis acid-base reaction. In this reaction, ammonia has a lone pair of electrons and boron trifluoride has an incomplete octet, since boron doesn't have enough electrons and around it to form an octet. Because boron only has 6 electrons around it, it can hold 2 more. Boron trifluoride can act as a Lewis acid and accept the pair of electrons from the nitrogen in ammonia, which will then form a band between the nitrogen and the boron. This is considered now an acid-base reaction, where ammonia is donating the pair of electrons to boron trifluoride, and boron trifluoride as an acid is accepting those electrons to form a new compound. H3NBF3. This is considered an acid-base reaction, where ammonia as the base is donating the pair of electrons to boron trifluoride, and boron trifluoride as an acid is accepting those electrons to form a new compound, ammonia borane, or formula H3NBH3. Because a Lewis acid accepts a pair of electrons, chemists call it an electrophile from the Greek meaning lover of electrons. They call the base a nucleophile or lover of nuclei because it donates the electrons to a nucleus with an empty orbital. In a chemical reaction, a nucleophile seeks a nucleus or a positive charge and an electrophile seeks electrons or a negative charge. Fundamental to organic chemistry is the fact that nearly all the reactions that you will study are reactions of an acid with a base, or more commonly, of an electrophile with a nucleophile. Note that in this formula of a new chemical bond, an electrophile accepts electrons and a nucleophile donates electrons. In these reactions, using a curved arrows shows the movement of electrons. In each reaction, a pair of non-bonding electrons from a nucleophile reacts with an electrophile to form a bond. All chemical reactions involve orbital interactions. The orbital description of a reaction can help you understand how chemical reactions occur. This is a molecular orbital picture of ammonia reacting with boron trifluoride to form a new bond. Being able to identify an acid or a base is important. Of equal importance is the ability to recognize how the structure of that acid or base affects its strength. The strength of a Bronsted-Lowry acid or base depends on the extent to which it ionizes in water. Although there are numerous solvents besides water, chemists discuss acid and base strength in relation to water because they use it so widely as a solvent. Chemists use the auto-ionization of pure water to determine the values for the concentration of acidic and basic solutions. Auto-ionization is the reaction of two molecules of water with each other to give a hydronium ion and a hydroxide ion. For this reaction, the amount of auto-ionization is extremely slight at 25 degrees Celsius. It is 10 raised to negative 7 moles per liter. The concentrations of aqueous cations and hydroxide ion are equal. That is, both measure to 10 raised to negative 7 moles. Chemists call this a neutral solution. If you add a compound that is more acidic than water, you increase the concentration of aqueous cation and makes the solution acidic. If you add a compound that is more basic than water, you increase the concentration of hydroxide ions and make the solution basic. To determine the relative strength of an acid or a base, you need to find out how much the acid or the base ionizes or dissociates in water at equilibrium. The equilibrium constant, or the Ke, gives this information and is defined as follows. Equilibrium constant is equal to hydronium ion positive multiplied by acid negative over hyaluronic acid multiplied by water. Because the hydronium ion concentration can span a very wide range of values from greater than 1 mole down to less than 10 raised to negative 14 mole, chemists measure the concentration of aqueous cation on a logarithmic scale called pH. The pH values gives the hydronium ion concentration of a solution. Therefore, measuring the pH of a solution is a means of quantifying the acidity of that solution. Chemists define this measurement as a negative logarithm, or base 10, of the aqueous cations concentration represented by the following equation. pH is equals to negative log 10 multiplied by aqueous cation. Chemists call Ka as the acid dissociation constant. The value of acid dissociation constant specifies the strength of the acid. The stronger the acid, the larger the amount of dissociation and the larger the concentration of aqueous cations. Thus, The stronger the acid, the larger the value of acid dissociation constant. Strong acid completely dissociates in water and have large dissociation constant. Most organic compounds are weak acids and have dissociation constants in the range from 10 raised to negative 2 to 10 raised to negative 60. Because acids have such a large range of values for their dissociation constants, chemists often convert those values to a logarithmic scale similar to pH. The following equation defines this scale. pKa is equal to negative log 10 acid dissociation constant. Here's a graphical summary of pKa values for some important categories of acids. It gives you an overview of the acid strengths of a variety of types of compounds. Here's another graphical representation of pKa values for some important categories of Bronsted-Lowry acids. Note that the value indicated for a functional group shows the most typical pKa value for members of that group. There are two relative strengths of an acid that can be determined using, first, the magnitude of Ka or pKa. As Ka increases, the strength of the acid increases, or as pKa decreases, the strength of the acid increases. Another relative strength of an acid is using structural trends. The strength of an acid, or Hx, depends on the electronegativity of the atom containing the acidic hydrogen. The stability of the conjugate base is X. You can also use this illustration chart to compare the relative strengths or some common conjugate acid-base pairs. The strongest acids are at the bottom left and the strongest bases are at the top right. The conjugate base of a strong acid is a very weak base, and conversely, the conjugate acid of a strong base is a very weak acid. An extremely important concept in predicting the outcome of a reaction is that the position of equilibrium is on the side of the weaker member of the acid conjugate base, or base conjugate acid pair. A strong acid or base is more reactive than a weak acid or a base. To summarize my report, here are some of the key ideas to remember about acid and base in organic chemistry. I hope you have learned something. Thank you and God bless.